In this lesson, we're going to look at basic magnets, starting first with the bar magnet. A bar magnet is a permanent magnet which produces a magnetic flux which flows from the North Pole to the South Pole. Here we have two magnets placed side by side, but if we focus on just the one for now, which I'll draw a box around here, we can see that the lines of flux flow from north to south. The more lines of flux a bar magnet, or any magnet for that matter, produces, the stronger the magnetic field. Interestingly, lines of flux cannot cross each other, and lines of flux can travel through the air and many different types of surfaces. If we look at this bar magnet here that's been placed on a metal table with iron filings, we can see that the filings are attracted to the magnetic poles, and as a result you can see that the actual filings from this area have been pulled to the North Pole and to the South Pole. So what we actually have here is we can see that the lines of flux, which are invisible but are there, are clearly demonstrated by the iron filings. And if you look here, you can see where the flux has effectively taken the iron filings and basically shaped them within the path of the flux. Now, magnetic flux, the symbol is phi and the unit is the Weber, WB. If we look at these three magnets' positions, so for these two magnets to attract, the poles, the North Pole and the South Pole, have to be opposite. So what would happen here is the flux would leave the North Pole, be attracted to the South Pole, okay, and likewise here the flux would leave the South Pole and be attracted to the North Pole. But what would happen is effectively the fluxes would join together, which would cause the two magnets to be pulled together in attraction. So that creates a mechanical force of attraction. When we have two magnets which have like poles, so north to north or south to south, they repel. That's because the lines of flux, as they come out of the bar magnet into the air, they effectively repel each other. So there is no way that the two can basically pull together. They are repelled. Likewise on these two south poles, so if we see there that the north goes from north to south, north to south, okay, we can see there that the two flux arrows basically would cause a problem and they would effectively pull the magnets, or should I say repel each other. So they would go in that direction and attraction. So unlike poles attract, like poles repel. That's an important statement to remember. So we're going to have a look at magnetic flux density now. And basically, if you see on the slide, what we have is I've sketched two bar magnets. Magnet A, I'll put an A on there, and magnet B. You can see per area, so the area here, on magnet A has fewer lines of flux than magnet B. So magnet B has more lines of flux per area, so this means that magnet B has more flux density. In other words, it's going to provide more magnetism. Now, magnetic flux density is very important in electrical engineering. Magnetic flux density, the symbol is B, and to calculate flux density B, it is phi over area. So remember from the last, so that is Weber's, which is magnetic flux, over area. Or, let's call that magnetic flux which is Weber divided by meter squared. So the formula basically is phi over area. The unit of magnetic flux can be Webers per meter squared, or it can be Tesla. T. Now B crops up in quite a lot of engineering, electrical engineering calculations, specifically motors and force. It's the fundamental principle of generation, because without magnetic flux we can't generate electricity in an alternator. Likewise, magnetic flux is also used in electric motors to provide a force, and we'll look at that in the next lesson. So let's look at an example. So if we look at this example here, we've got a magnet that's got a cross-section area of 25 millimeters length by a height of 10 millimeters. So we're going to need to work out the area. The flux of the magnet is 15 milliweber. So as always, the first thing we do is we write down the formula. Formulas are like tools. If we remember the formulas and we apply some basic maths, we can get the solution. So we're going to work out the magnetic flux density of this arrangement. So the first thing is, we know that phi in the question is given as 15 milliwebers, but be careful because that's a prefix, so the actual value is 15 times 10 to the minus 3 Webers, or if we can move decimal places, 0.123 Webers. I always like to use standard form, so I tell students to remember the SI prefixes. Milli is minus 3, micro is minus 6, nano is minus 9, and pico is minus 12. Get into the habit of remembering the prefixes. It's very important for accuracy. The next thing we're going to work out is the area. Now, obviously, the SI unit for length is the metre, not the millimetre. So we're going to work out the area first in millimetres. So that's simply 10 millimetres times 25 millimetres, which is 250 millimetres squared, because we've got millimetre times metre. Now, basically, to convert that to metre squared, it's minus 3. So milli is minus 3 plus minus 3 because it's squared. So the actual equivalent area in metres is 250 times 10 to the minus 6 metres squared. So all I tell my students is if you see the milli sign and it's squared, then it's simply minus 6. If it was millimetres cubed, then it would be 3 times minus 3, which is minus 9. Okay. So 2 times minus 3 is minus 6. Okay. Drop that into our formula now. So B is going to be 15 times 10 to the minus 3 over 250 times 10 to the minus 6. Okay, and that basically, so we can simplify that. So we can say the minus 3 off minus 6, so that's going to be 15 over 250 times 10 to the minus 3. So that's going to be 15, just work that out, divided by so what we have now is 15 over 0.25, because obviously we've got 1, 2, 3. So 15 over 0.25 is 60 Tesla, or 60 Bebers per metre squared. Very straightforward. So the key points in this question: identify the units, phi, Bebers, area, metres squared. In the question we can see it's in millimetres, so we're going to need to convert millimetres to metres before we put the numbers in our formula. So this particular magnet would have a flux density of 60 Tesla, or 60 Bebers per metre squared. Let's look at another example. So in this question we've got to calculate the required magnetic flux to achieve a Tesla of 45 for a magnetic area of 200 millimetres squared. So what we do here is, again, recall the formula. The more you do it, the more you remember. And we're going to rearrange the formula for phi. So if we get what we want to make phi the subject, so we times area on that side. What we do on that side, we do on this side. Okay, so area goes. So basically, invert the formula. So phi equals B times A. So in the question, pull the answers out. So B is Tesla, so that's 45. The area is 200, but remember that is in millimetres squared. So to change that to metres squared, we have to change it from 200 to 200 times 10 to the minus 6. And we simply push that into our calculator. So 45 times 200 times 10 to the power of minus 6 gives us 9 times 10 to the minus 3 Weber, or 9 milli Weber. Okay. It's not often you will use this formula, to be fair. We do use magnetic flux density mainly as the main part of magnetic calculations in motors and generators. But this is just a theory to show you what flux density is that the more magnetic flux there is per area, the bigger the flux density. In other words, the more power the magnetic field. Okay, thanks for watching. What we'll do in section 2, magnetism, is we will look at force on a conductor. Bye for now.